Howdy.
Howdy.
Today we have a guest speaker was the TLAC from TLAC series, and Dr. Knuth from University of Wisconsin-Madison. And actually, Dr. Mary Margaret Capero initiated the invitation. So, Mary Margaret, you possibly know better about Eric, so you would like to come to say something about Eric and introduce him?
No, that's okay. He'll just going to introduce himself.
Well, I think evening's passing the blame. In case you don't enjoy the talk, you can blame Mary Margaret.
Oh, you are so fast thinking. Eric actually has been a great scholar actually in math education in this country, and people know much about him, and he has been doing wonderful work in algebra and also proof of the years, and he also has been actually doing the great job in kind of leading the math ed group at the University of Wisconsin-Madison, and University of Wisconsin-Madison math ed group actually has quite some reputation in this country. So we are fortunate to have this opportunity to learn, what Eric has been doing, and it's also opportunity for you to share possible your work as well. You can stay right after talk. You want to talk with him a little bit more, and also feel free to ask a question as well. So let's welcome Dr. Eric Knuth.
Well, it's a pleasure to be here. I'm kind of curious, just in terms of audience, how many of you are math education folks? Okay, so I just wanted to make sure I was talking to people that may have some background knowledge about some of the math education research and early algebra that I'm going to be talking about. So the title of my talk is The Impact of Early Algebra on Students' Algebra Readiness. And I also want to acknowledge my collaborators on this project, Maria Blanton at Turk, and then Anna Stevens, also at the University of Wisconsin in Madison. So first, I'll give some background on kind of the algebra problem, as I'm calling it, and this should be no surprise to any of you, whether you're a math education person or not. But the main problem is that many students are unsuccessful in algebra. So that's been going on for decades, that students have a hard time with algebra, and part of the difficulty then leads to its gatekeeper role in future educational and employment opportunities. So lack of success in algebra cuts students off from a lot of potential further study and career opportunities. And I think it's pretty clear that the arithmetic that students study in elementary school does little to prepare them for success in algebra by the time they hit middle school and high school. And so what I'm going to be talking a little bit about today is the solution to this algebra problem. And so the solution that I'm going to be talking about is, as you may have guessed from the title of the talk, early algebra. And so what do we mean by early algebra? So it's not just a matter of taking the first year algebra course from high school and kind of just moving it down lower in the grades, and so that's early algebra. But in this case, it's really thinking about algebraic thinking as a K-12 strand, so integrating ideas from algebra throughout the curriculum, not just when students get in pre-algebra or the 9th grade or sometimes 8th grade first year algebra course. The idea is also to build on students' informal intuitions and their about patterns and relationships that they come into school with. And the other key is that it needs to be long-term and sustained. So it's not just something you can kind of in one single course or unit kind of give students some algebra and expect, okay, now they've got what they need to be successful when they reach more formal algebra in the middle grades or high school. And I should also say, if you've got questions at any point, you don't need to hold them to the very end. If you've got a question about something, feel free to interrupt as I'm going, so you don't forget your question or if you need clarification on something. And another important part of early algebra is that it does not take away from learning arithmetic. So a concern that sometimes is brought up is that there's no more room in the curriculum, whether it's elementary school, middle school, high school, that it's already a pretty dense curriculum, and putting more in, there's really not space. Something's got to give. And so one of the things that folks that are advocates of early algebra feel that it also supports the development of what they're supposed to learn in elementary school, some of the arithmetic understandings that we want students to learn. So early algebra is designed to support that, and if anything, help them learn that in even deeper ways than they might normally. So real briefly, I want to just talk about some of the research that's been done in early algebra to date. So there are a number of people that have focused on early algebra research, and I'm going to characterize each of the kind of programs of research pretty briefly. So there's certainly more entailed than I'm going to kind of talk about, but some of the highlights from the different programs. So Tom Carpenter and his colleagues have done a lot of work with student understanding of the equal sign. And so by that, I mean, so oftentimes students think of the equal sign as an operation to do something. So it may be lots of experiences with, 3 plus 7 equals blank. And so the equal sign signifies the answer comes afterwards. And so that's how a lot of students view the equal sign. And where they run into difficulty, if they've got an equation like 3 plus 4 equals blank plus 2, many students will put the 7 in the blank, thinking after the equal sign comes the blank, and they don't look at it in terms of a relationship, an equivalence relationship between quantities. So they look at one side as being the same as the other side, and they don't just see the equal sign meaning something comes next. And so Tom and his collaborators have done a lot of work looking at the development of that idea in elementary students. There's also Deborah Shifter, and some of her colleagues have focused on generalized arithmetic. So looking at regularities and patterns in arithmetic operations, for example, noting that it seems like when I add 0 to a number every time, I just get the original number back, or looking at some of the fundamental properties of arithmetic, recognizing those kinds of regularities in the calculations that students often do in elementary school. There's also this idea of representing and symbolizing. So David Carragher and his colleagues have been working on helping elementary students develop their ideas, understanding graphs, and using variables to represent unknowns. And then Maria Blanton and Jim Caput and colleagues have been working on functional thinking, so helping students to understand what it means to have quantities, covariant quantities, and to understand how to work with functions of that sort. And then finally, Barb Dougherty and her colleagues have been doing a lot of work with reasoning about abstract quantities. So if you're familiar with the Russian mathematics curriculum, the Davidov curriculum, she's utilizing that in schools and building on the ideas about reasoning about abstract quantities. And again, the point about the early algebra research is all this is happening in the elementary grade. So it's not, all this work that I'm just citing is primarily 3rd, 4th, and 5th grade is where most of the activity has happened, although some of the people are also working K2. And so the question that I want to address is, does early algebra matter? And the question you might ask is, matter for what? And so part of what I'm going to be talking about today is that early algebra doesn't matter for students' later success and preparation for algebra. So one of the issues with the current research in early algebra is that it hasn't been sufficiently comprehensive in the treatment of algebraic content. So as I outlined on the previous slide, there's different researchers that have focused on particular aspects of algebra content. So whether it's the equal sign or generalized arithmetic or functions, but it hasn't been comprehensive in the study. And so that shouldn't come as a surprise for research programs to focus in on particular aspects to learn in depth about how students think about it, how teachers think about it, how to design curriculum to support students' understanding. But the issue, again, is that there hasn't been a kind of comprehensive look at, okay, can we package all of this together and look as a whole, how does this treatment of early algebra ideas impact what students learn and how well prepared they are for algebra? It also, this research hasn't been sufficiently longitudinal, and so much of it is focused on individual grade bands, so it may look at grade 3 students, and that may be who the researchers work with, or a limited grade span, so maybe grade 3 and 4 students, or grade 3 and 5, but it hasn't really looked long-term at early algebra in grade 3 through 5, and then how do those students do as they enter middle school, for example, when they're getting into the more abstract algebraic reasoning required for middle school. Another issue with some of the early algebra research is that it's typically been researcher-led or researcher-supported early algebra interventions. And so oftentimes, if they're implementing new early algebra curriculum, it may be a member of the research team that's teaching the curriculum, or there's a lot of extra professional development support that the teachers are getting, so they may be implementing the curriculum or the ideas in their own classrooms, but the research team is providing a tremendous amount of professional development that wouldn't occur in more naturalistic type settings. There's also been very few studies that have compared student performance, and by that I mean looking at, okay, if we have students that are going through an early algebra curriculum, how do they compare to students that went through a typical arithmetic elementary school curriculum? Do they perform differently in regular mathematical concepts and ideas? Do they perform any differently when it comes to some of the early algebra concepts and ideas? And so there's been very few studies that have looked at this comparison among kind of students who go through the typical curriculum versus those who go through an early algebra curriculum. There are some research findings that are suggestive that early algebra makes a difference. So for example, my colleagues and I, in our work with middle school students, showed that students that have a relational understanding of the equal sign, so that's viewing the equal sign as an equivalence relationship between quantities, actually perform better in solving kind of algebraic equations and tasks that are more kind of what we think of when we think of algebra, compared to students that don't have that kind of understanding, which suggests students in elementary school, if they are given opportunities to develop this relational view of the equal sign, they're more likely to be more successful when it comes to some of the traditional activities of algebra. So the bottom line is there's still this open question about what is the impact of a longitudinal, comprehensive early algebra education on children's algebra understanding and the readiness for algebra in middle school. So there really haven't been any studies to date that have really looked long-term at students that are going through an early algebra curriculum. How well prepared are they by the time they hit algebra in middle school or ninth grade algebra? Part of the reason for this has to do with the research programs, and the funding is often very limited. So if NSF, for example, provides 3 to 4 years of funding, one can't follow students 3rd grade, 4th grade, 5th grade and continue for that long term without securing extra funding, which you're never guaranteed that you're going to have that kind of funding for such a long-term study. So the focus of my presentation today, I'm going to talk about 2 different NSF-funded early algebra projects. The first project just recently ended, was a 3-year project in which my colleagues and I developed a grades 3 through 7 early algebra learning progression, associated assessments, classroom lessons, and professional development materials. And so and I'll talk more about each of these projects in a moment. But that was the goal of that project, was just to develop this comprehensive early algebra program, the lessons that would accompany the curricular progression, and then the professional development that would help teachers be prepared to implement the early algebra learning progression. And the second project, which has recently started up, is using a quasi-experimental design to actually test the efficacy of the early algebra progression. So by that, I mean we're implementing the early algebra curriculum in a number of elementary schools, and then we're following those students into middle school, and we're looking at how their algebra understanding, as well as their kind of typical mathematical understandings that we would expect students to acquire as they go through the school, how that compares with students that went through a more traditional arithmetic curriculum.
Eric,
Yes.
when you talk about those 2, can you tell us, because there's a lot of people interested in applying for grants and stuff, was the first one like a developmental grant and then it led into that? There was one more money than the other? Was one a level 1 or 2, or how that works?
No, well, to be honest, when we applied for the proposal we put together for the first project, actually was both project 1 and 2 combined, and thankfully NSF convinced us that we're biting off more than we could probably chew. By that I mean developing the learning progressions, the assessments, the curriculum materials, and the professional development, and follow students through this progression. And so they wanted to also see, because there really hasn't been any data to suggest that it does make a difference. So as part of the project 1, we developed the learning progression and on a small scale tested the efficacy of it. Were students both kind of able to learn some of these concepts in grade 3 where we started, and were teachers able to implement some of these ideas without tons of researcher support? And so that was the NSF then again convinced us, okay, why don't you just develop the learning progressions, assessments, and materials, get some data that suggests it looks like it might work, and then didn't promise us grant 2, but suggested if you've got good results from project 1, the likelihood of getting funded for the follow-up is higher. And so that's where we are. So it was really meant to be originally one project, and then the second project, then when we put that proposal in, it was to actually carry out the experiment where we could compare traditional instruction to our early algebra instruction.
Okay, thank you for clarifying.
So I want to talk briefly, and I'll try to judge by if any eyes are glazing over or closing to know either to skip through some things or try to liven it up a bit. But again, if you've got questions, let me know. But I want to talk a little bit about Project 1 in terms of what we meant by a learning progression, how we went through some of the details that are in the learning progression, so you have a sense of the early algebra curriculum that we kind of developed. And by curriculum, I'm not talking kind of a year-long, and I'll get into that shortly, but it wasn't, here's an early algebra textbook that now teachers can implement this curriculum, but rather there were early algebra curriculum materials that were meant to be integrated into the whatever curriculum that the teachers were using.
Was this, I can think of the curriculum for these grade levels, for a state or whatever, so it's got a progression to it of some sorts, and the normal number sense, variables, all of the stuff that goes in there. And then you've got a set of ideas here related to what algebra goes in there, kind of, it's a matrix. So is that kind of the approach you took? How are we going to try to fit these together into those so that they flow, sort of?
Yeah, so that's part of the challenge with the early algebra, developing early algebra curriculum materials, is that not every school in the United States is using the same curriculum where we could say, okay, this is where it fits in. And so it's really a matter of thinking about how teachers might integrate this into their curriculum in ways that wouldn't be kind of, okay, today's early algebra day, the other 4 days are arithmetic and Fridays are early algebra day. That's not the kind of add-on that we wanted, but we wanted teachers to kind of, yes, there are particular materials that we develop, but it's also a way of seeing their arithmetic curriculum. So thinking about, when they're doing calculations, maybe and working on their number sense, that they're also having opportunities to talk about the equal sign, for example, or looking at some of the regularities in the calculations that they're doing and trying to generalize some of these ideas and coming up with things like commutative property of addition. And so looking for opportunities. And a way what Jim Caput used to talk about is developing teachers' algebraic eyes and ears. And so that's part of what we're thinking about is looking, helping teachers to learn to capitalize on those opportunities to engage students in algebraic thinking with their regular curriculum. And this is meant to, in some ways, be a catalyst to help kind of provide explicit opportunities, but also to help them think about the other ways that they might kind of integrate it into their curriculum. So we developed this curriculum around learning progressions, and so in math ed, it's more typical to talk about learning trajectories. There's a lot more research within math ed that speaks to learning trajectories. Science ed, there's a lot more about learning progressions. And I'm not going to talk in much detail about the pros and cons of one approach versus the other. The learning progressions, however, in our interpretation of learning progressions, are often looking at larger scale. So the grain size issue is a little bit different with learning trajectories, is often much more focused on particular topics. And we're looking at early algebra across a span of grades 3 through 7. And so we're looking at kind of how these big ideas progress from grade 3 to grade 7, thinking, okay, 8th grade would be in many places where they start first year algebra. So as the National Research Council defines it, a learning progression is meant to provide an ordering of concepts, understandings, skills that build towards a more sophisticated understanding of an important idea or topic. That's actually not too different from how you might characterize a learning trajectory, but again, part of the idea is the grade span is much larger than that we're working with, as well as the grain size of the topics. We're looking at early algebra versus many, like there's learning trajectories that have been developed in the area of measurement, for example. And they may look at, in grade 4, how students' ideas of measurement, progress from particular levels to more sophisticated levels. So some of the key characteristics of the learning progression work that we're doing, so it's based on the logic of the discipline, current learning research, and curricular frameworks and standards. And I'll talk a little bit more about this aspect of it in a moment. It also specifies lower and upper anchor points. So, for example, thinking about in grade 3, with the equal sign, what is it that we want students to be able to understand about the equal sign in grade 3, and where do we see that when they hit grade 7? What should they understand about things like about the equal sign? It also specifies grade level competencies and connections among them. So how do they transition, and what does that transition of understanding look like as they progress through the grades? It also informs the design of appropriate instructional strategies and learning tasks. So how do we design tasks that help students progress along this continuum? And grade level assessments that allow teachers to measure where students might be along this learning progression. And finally, also identifies key transition points. So in grade 3, or not necessarily by grade, but there might be key transition points in a student's understanding of variable that are very critical to making the next part of the progression. So I want to talk now about some of the process and components, and I'll be coming back to aspects of this as I go into some more detail. But one of the first things we want to do is identify the big idea. So early algebra. So what is entailed in early algebra? There's lots of algebraic ideas and concepts that we might think about. And so we identified particular big ideas that were going to be the kind of grounding points for the learning progression. We then also identified constructs that were necessary to understand the big ideas. So particular understandings that we wanted students, where we created these claims that specify the nature of the knowledge, skills, understanding expected of students regarding a particular construct. Specify the evidence, so from the student work that would indicate that a student has acquired that particular understanding or knowledge or skills. Also identify what kind of difficulties and misconceptions do we expect students to have at particular grades in the progression. And then finally also looking at the research base that supports the different claims. And so one of the things with learning trajectories that is often the case is that they're hypothetical, and researchers will go in, test something out, and look for shifts in the students' understandings. Here we were building from what do we know about the previous early algebra research that I mentioned earlier. What have they found out about grade 3 students thinking about the equal sign, or about functions, or about variables? And then what do we know from the research about grade 4, and kind of piecing this together into the progression. So the progression we came up with was based on our synthesis of the research on teaching and learning algebra across grades K-9. So looking at, again, the research base on what we know about the teaching and learning of algebra. State and national learning standards and frameworks, so things like the Common Core, NCTM standards, various state frameworks on looking at how they sequence some of this algebraic ideas, what grade levels they see it as appropriate, and so forth. We also looked at a variety of elementary and middle school curricula to look at how different algebraic ideas were treated in these curricula and at what points in the curriculum. And we also looked at mathematical perspectives on algebraic content. So if we look from a purely mathematical perspective, how are some of these ideas sequenced? What are the precursors to particular concepts, and where does that concept then build next, again, from a mathematical perspective? And so we came based both on our reading of the former things as well as what's been talked about in the literature. We came up with 5 big ideas that we were focusing our early algebra work on. So generalized arithmetic, equality expressions, equations, and inequalities, functional thinking, variable, and proportional reasoning. And I also want to point out that these aren't meant to be mutually exclusive. So obviously variable plays an important role in equations and in representing functions. So again, we parsed it this way, but there are lots of interconnections still among these 5 ideas. So again, they're not distinct and unique 5 ideas. And they're not unique in the sense that another group of researchers may parse different ideas. And so this isn't meant to be kind of this is the way it has to be, but this was the approach that we took based on our work leading to this point. We're also looking at kind of particular practices that we thought were essential to algebraic thinking. And so these were based on some of the work from Jim Caput. So the 4 practices that we also used in addition to the big ideas were generalizing relationships, expressing relationships, justifying generalized relationships, and reasoning with relationships. And maybe as you can tell just from the little that I presented so far, that NSF was probably correct in telling us, you were biting off more than you could chew to think about doing all this on top of doing efficacy study to look at the effect of the early algebra. So putting it all together, we developed tables that identified the constructs, claims, evidence, difficulties, misconceptions, and the research base within each practice for the big idea. And I'll show you what that looks like in a moment. And then we also had a grade-by-grade progression. So we went from grades 3 to 7, again thinking in many schools, 8th grade is where algebra begins. So we were going up until the point of formal algebra. That details how these big ideas develop or can be developed across the grades, what content would be developed at a particular grade, and what skills and understandings are expected for that particular content. And so the grade-by-grade progression is hypothetical in the sense that, as I mentioned earlier, there really haven't been any longitudinal studies of these ideas looking at, okay, if students in grade 3 develop these understandings, what happens in grade 4, what then happens in grade 5, what would happen in grade 6. And so at some point, we're thinking, okay, based on if students develop these understandings in grade 3, what might we expect in grade 4? What could we expect in grade 5? What could we then expect in grade 6? So it's really based on the premise that students are having a very different elementary school experience than they traditionally do. And so this is kind of a picture of what this looked like. So algebra at the top is the early algebra. And then we have our 5 big ideas, the functional thinking. EEEI is not old McDonald song, but the equations, equality and expressions and so forth. Generalized arithmetic, variable and proportional reasoning. And so then there were the 4 strands, so the mathematical practices, so generalizing relationships, justifying relationships, so those were the strands. And then within each strand, we develop the constructs for that particular strand under functional thinking. So it's pretty complicated. I think, if you're interested in looking at more detail, I'll put up our website URL at the end, but we've got all the learning progressions up on our website, and they're, for each big idea, it's probably 40 pages worth of information. So, they're pretty detailed when you can imagine going through for functional thinking, all the various constructs, and this is by 1 grade, so grade 3, then you'd have that for grade 4, 5, 6, 7, so it's quite involved. So that's the extent of the detail that I'm going to go into for the first project. I'll tell you a little bit about some of the project outcomes. So as I mentioned, we've come up with articulation of a grade 3 through 7 early algebra learning progression. So we've provided those details of what happens in each of those grades across each of these big ideas and thinking practices. We've developed a set of validated assessments based on the early algebra learning progression. So we developed these assessments and then psychometrically tested them in the schools to validate the assessments, both the construct validity and their reliability. We've designed a series of classroom lessons that are based on the early algebra learning progression. And we've developed professional development materials based on the early algebra progression. So this was kind of, at the end of the 3 years for Project 1, this is what we have to show for it. And then we started on the second project, which is then the follow-on to the first one. So the main goal of this second project was to test the effectiveness of the early algebra learning progression. So we wanted to know, okay, does this work? Does it make a difference? Are students any more prepared for success in algebra by the time they hit middle school? So as I mentioned earlier, it was a quasi-experimental design. So we've got a number of treatment classrooms in which students are receiving the early algebra curriculum, and then the controls classrooms in which students are just receiving kind of business as usual curriculum, so just what they would normally experience. So we're implementing the early algebra learning progression in grades 3 through 5. So even though we developed this progression grade 3 through 7, we're looking at the most impact, trying to make a difference in the elementary school experience for students. And so we're looking at, does a grade 3-5 early algebra intervention have long-lasting and positive impacts on students' algebra readiness? So our plan is we're following both the control and experimental students starting in grade 3, and we're going to follow them into grade 7. And again, only grades 3, 4, and 5 are receiving the experimental curriculum. In grades 6 and 7, they're going to experience whatever curriculum they're experiencing at the particular middle school that they're in, with the idea being that the grade 3 through 5 experience should have differential outcomes for these students when they hit middle school. So we're following the cohorts of students. We're implementing the pre and post tests at the beginning of 6th grade, end of 6th grade, beginning of 3rd grade, end of 3rd grade, and beginning of 4th grade, and so forth, all the way through grade 7. So the data that I'm going to share today, since the second project is just recently, we're a year into it now, so I'm going to share some of the data. So we gathered data. This is from a sample of our schools, and so we've got about 300 students in this sample that I'm going to share, grades 3 through 5 from one school district. So there were 10 control classrooms and 6 experimental classrooms. In the larger sample, I think we have about 25 control classrooms and about the same number of experimental classrooms. So I'm just sharing data from the first smaller subsample of schools because that's all we've had a chance to analyze at this point.
What was the nature of the teacher training for the experimental groups? Did they work with you, or was it like summer presentations, or?
Yeah, in part of the first project, we worked with teachers at the districts that are implementing the experimental curriculum, and so we had one of our project staff was teaching lessons at the 3rd, 4th, and 5th grade in these classrooms with the early algebra materials, and then the team was providing professional development for teachers at school during the school year, including the summer component as well. Yeah, I haven't said we're also collecting fidelity of implementation data as well, so we have an idea, you know, if teachers really are implementing the early algebra curriculum as intended, or are they doing something different. So that's data for another talk.
Are you doing any videoing with it, or are you just observation?
You know, part of the, as many of you may know, part of the difficulty with video data is getting the consents, and it makes it difficult if you don't have 100% consent, and the number of schools we're in, it just became too complicated of a problem to try to really deal with the IRB issues associated with the videotaping.
And what was the justification you did intervention 3, 3rd, 4th, and 5th grades, but you did not do intervention on 6th and 7th grade, right?
Right.
And then when you also, another question, when did you give the post-test? I mean,
The post-test is at the end of each school year.
each school year.
Yep. So the pre-test right at the beginning before kind of instruction really starts, and then the post-test at the end of the school year towards the latter, you know, towards the end of instruction each year.
6th and 7th grades as well?
Yeah, 3rd, 4th, 5th, 6th, and 7th. Well, that's the plan that we'll continue to be doing that.
And why didn't you do intervention during 6th and 7th grades?
Well, so one of the things happens to be based on how early algebra has typically been defined. It's usually been kind of the elementary school focus, and so we're really looking at much of the work that goes on in the elementary schools. What we're finding is, you know, as I mentioned earlier, that arithmetic does little to prepare students for the kind of abstract algebraic thinking required for middle school and beyond. And so one of the things we're hoping we can get more bang for the buck by looking at what if we really do something in elementary school, and even if students go on to just whatever middle school, so everyone's receiving the same middle school instruction, but the early algebra experience for those students will make a difference in how they understand what they're learning in middle school and will have dividends, regardless of. So that was part of it. The other part was just resources. It's just too difficult to, with a small research team to manage that size of a project. So the data that I'm going to share this afternoon is just going to be from the grade 3 data. And part of this has to do with, we collected cross-sectional data, so we do have the data from the 3rd, 4th, and 5th graders. But the curriculum, the early algebra curriculum for the 4th graders, they haven't experienced the 3rd grade curriculum yet. And so we're really just finished the 3rd grade intervention last year, and now we're doing the intervention in the 4th grade with those same 3rd grade students. And so, sharing the data from the grade 4 students at some level doesn't make sense because they didn't have the grade 3 experience, and the grade 5 students didn't have the grade 3 or the grade 4 experience. And so I'm just going to be sharing data from the grade 3 students, and I'll allude a little bit to the cross-sectional data when I want to make a point about what we're seeing. So in this particular case, I'm going to share the data from 23 early algebra lessons. So it was 1 hour per week for essentially the school year, when you take out vacations and other shortened weeks. And in this case, I'm going to be looking at the best case scenario. So we're looking at the lessons were taught by a member of our research team. So the data that we're gathering includes, as I mentioned earlier, it's more naturalistic, and then we're looking at what teachers are doing, regular classroom teachers. But in this case, we're kind of looking at the best case scenario. If we don't see improvement in the best case scenario, then it's likely we're not going to see anything with regular classroom teachers who don't have the same kind of background that our research team member, who's a former elementary teacher, that's doing the instruction.
And how many hours they were receiving math per week?
Just whatever, so both the control and the treatment, I don't remember the hours off the top of my head, but both control and experimental students were receiving approximately the same number of hours per week for the entire school year. So the early algebra wasn't, an extra math, each week, but it was just built into the curriculum that they were doing. And again, we gave the 1 hour assessment, was given as a pre-test, and then the same assessment again as a post-test at the end of the year. And we have, it's not the same, so 3rd graders, 4th graders, 5th, 6th, 7th, it's not the same assessment given to each grade level. There are core items that cut across grade bands so that we can see, the development as a student progresses from grades 3 to 4 and 5. There may be the same item where we can see, but giving a student, in 7th grade, one of the items that's appropriate for a 3rd grader, doesn't make sense. So the same big ideas, same constructs are being addressed, but as we expect students' understandings to become more sophisticated, then the assessment items also become more sophisticated. So just some of the real brief big picture results. So at pre-test, there were no significant differences between experimental and control students. So they essentially looked the same in their math ability. At post-test, the experimental students significantly outperformed the control students on all of the items on the assessment. And this is statistically significant results. And the grade level did not significantly impact post-test performance. So by that I mean, if we look at the performance of the grade 3, grade 4, and grade 5 students on the assessment, the grade 3 students did as well as the grade 4 and 5 students. And by that, what we take from that is meaning that the curricular experiences were appropriate for the 3rd graders, that it didn't require more advanced mathematical knowledge that a 5th grader may have compared to a 3rd grader, that the curriculum materials were appropriate for the 3rd graders, and that having more advanced kind of arithmetical knowledge at that point of a 5th grader's education didn't make a difference in terms of they did better on these early algebra ideas. So that highlights again that the curriculum materials was appropriate for the 3rd graders, but also it also highlights that the arithmetic curriculum does little to improve student understanding of some of these algebraic ideas, because the 5th graders really didn't do any differently than the 3rd graders did on the algebraic items. So their arithmetic that they learned in 3rd, 4th, and 5th grade did little to help them better understand some of these algebraic concepts. So I want to just share some of the items and some of the results just so you can have a sense of some of the assessment items and what we're looking at. So here's some sample items from the kind of equal sign, expressions, equations, and inequalities. So this is the first one's a pretty typical one when people are looking at student understanding of the equal sign. So fill in the blank with the value that makes the following number sentence true. How did you get your answer and why? And so, as I mentioned earlier, for many students, the answer to this that goes in the blank is 10. So they look at the equal sign, answer comes after the equal sign, so 7 plus 3 is 10, and they put a 10 in the blank. Students with what's often called a relational or structural understanding of the equal sign will look at that and think, well, it's 7 plus 3, there's a couple ways they can approach it. They can calculate, so they can say that's 10 on the left side, I need to have 10 on the right side, so 6 has to go in the blank. Or they can do it as a more kind of compensation idea, so they can think about, well, 4 is 1 more than 3, so I need 1 less than 7, so I need 6. And so they really don't do a calculation, but they're thinking about the equivalence relationship. And likewise with the second one, circle true or false. So for many students, the answer is false because 57 plus 22 does not equal 58. Other students may calculate, decide yes, left side equals the right side, or they can use that compensation strategy that I mentioned with the previous one. So if we look at some of the results, so again, at pre-test, there was no significant difference between experimental and control students on either item. And so this graph is just showing success, so whether they answered correctly or not. And experimental students significantly outperformed, as is pretty apparent by the graph that you could guess that it's a significant difference. If we look at some of their strategies, so both groups on pre-test were primarily used an operational strategy, which again means answer comes after the equal sign. At post-test, 77% of the experimental students used a more relational strategy, that they did not use the answer comes next strategy for figuring out the answer. So over 3/4 of the students looked at it more relationally. They either thought about equal sign means same as, same quantity on both sides, and so they used some strategy that utilized that, while only 13% continued with the operational, versus the 90% of the control students still did that on the post-test. So there wasn't a whole lot of change for the control students, that they still tended to think operationally about the equal sign. And then same thing went on the second item, that the majority of students from the experimental group used a non-operational strategy, where 50% of the control students still used the incorrect operational strategy. So here was a sample variable item. So Tim and Angela each have a piggy bank. They know that their piggy banks each contain the same number of pennies, but they don't know how many. Angela also has 8 pennies in her hand. So they were asked a number of questions about this. How would you describe the number of pennies Tim has? With the idea being that a student might assign some variable, like P would stand for the number of pennies that Tim has. Part B, how would you describe the total number of pennies Angela has? So again, a student might respond, if P was how many Tim had, then P plus 8 would be how many pennies Angela had. And then finally, if they combine their pennies, how would you describe the total? So a student with an algebraic understanding might do P plus 8, or kind of one way to represent that. And again, we didn't see any differences at pre-test. On post-test, the experimental students significantly outperformed the control students on all 3 of the variable items. And if we look at some of their strategies, at pre-test, neither group used variables for the responses. So they may have provided some description, but didn't actually use a literal symbol. So at post-test, 3/4 of the experimental students used a variable to represent a quantity. So in part A, they may have said P stood for the number of pennies that Tim has. At post-test on part B, 3/4 used variable expressions again, and 63% used a related variable. So by that I mean the 74% who used a variable, it could have just been, okay, on part A, they said P stands for the number of pennies that Tim has, in part B, which was Angela has 8 more than Tim, maybe they put X down for the number that Angela has. So there was no relationship to the first one, but they just expressed it as an unknown, where 63% of the students used a related variable. So if P stood for the number Tim had, then Angela had P plus 8. And finally, in part C, 58% used variable expressions from the treatment, and 40% used related variables. So again, something like P plus 8, where none of the control students do that. A sample generalized arithmetic item. So Evelyn computes the following: 8 minus 8 equals blank, 12 minus 12 equals blank. She gets an answer of 0 each time. She starts to think that anytime you subtract a number from itself, the answer is 0. Which of the following best describes your thinking? Circle your answer. And so in this one, we're looking at, can students kind of both utilize variables, but then also generalize the identity that's taking place here. If we look at the grade 3 performance, again, no significant differences at pre-test. Experimental students outperformed control students at post-test, and they seem better able to interpret the equation with variable expressions. So they were able to use the natural language and the symbolic language more easily. And finally, just looking at a functional thinking item. So here we're looking at a problem where Brady is having his friends over for a birthday party. He wants to be sure he has a seat for everyone. He has square tables. And so they're given the examples. You can see 4 people at a square table in this way. And then he joins 2 tables and he can fit 6 people, with the idea being, can students come up with a functional relationship? So they were asked a number of follow-up questions. So if he keeps adding square tables in this way, how many people can sit at 3 tables, 4 tables, 5 tables? And students were provided a chart to complete. So we're also looking at, can they interpret the tabular representation, and then can they complete it correctly? They were asked, do you see any patterns in the table? So we were looking primarily, did they notice kind of recursive patterns? So if we look strictly in the number of tables, did they see what's going on? Did they look at the number of kids, what's going on? Or did they look at the covariant quantities? And then can they find a rule that describes it? Can they describe it in words? And can they describe it in symbols? And so I know it's probably can't read the details on the graph below, but the main points, again, no significant differences at pre-test, and then the experimental students outperformed control students on all parts of the test. So both filling in the table correctly, noticing either a recursive or functional relationship, being able to express it in words, being able to express it in variables. And they were also asked kind of a far transfer item, so asked the question of if he has 10 tables, how many you can see, with the idea being that's a little bit further, probably less likely that students will continue to fill out the table and try to utilize some rule for figuring out the case. So just some preliminary findings at this point. So there were significant pre to post-test gains for the experimental students' ability to think relationally about the equal sign on all of the items. Control students on the equal sign type items still continued to think relationally. There were significant post-test gains in students' abilities, experimental students' abilities to meaningfully represent unknown quantities with variables. None of the control students used variables in any way on the pre-test or post-test. Experimental students were more likely to recognize the underlying structure of fundamental properties, so things like the commutative property, identities, and they could use that as a basis for justifying generalizations. Experimental students were better able to interpret equations with variable expressions and to navigate between representations, so using natural language and symbolic representations, for example. The experimental students outperformed control students in their ability to identify and describe function rules in both words and variables, and they were more likely to use variables to represent their rules. And finally, the experimental students increasingly used strategies that were more algebraic in nature, while the control students did not. So at some level, a natural question, and one that would be expected, is that, sure, you would expect the experimental students to do better. I mean, they had a curriculum that targeted the ideas on the assessment, so of course they're going to do better. Part of our interest in doing this is to both show that elementary students can successfully develop the breadth of algebraic thinking skills that are necessary to be successful for algebra in the later grades. So a lot of the early algebra research, as I mentioned earlier, focused on particular elements. So looking at third grade students' understanding of the equal sign. And another program of research might have looked at different students in grade 4 and their understandings of variable. So one thing we were interested in is if we put it all together in a comprehensive kind of early algebra approach, are grade 3 students able to handle that in a sense? I mean, is it, it's not beyond what they can reasonably learn to do. It also highlights that the business as usual approach, by that meaning the traditional arithmetic curriculum, does little to prepare students for success in algebra. It doesn't, at least the data that we have suggests that it does very little to help students develop an understanding of these fundamental algebraic ideas. Both in 3rd grade, 4th grade, and 5th grade, we saw similar results in the assessments that we gave the students. And so I think that's another kind of important point to make, is that if we want students to be successful in algebra, we really need to start providing some of these early algebra experiences much earlier, because the standard arithmetic that they're learning in elementary school does little to support that kind of development of their understanding. And so certainly as we continue in our program right now, when we're collecting data on the 4th graders, then the 5th graders, where we really hope to see that it makes a difference is when these students are in 6th and 7th grade, where we can look at how they're performing in both their classrooms and on the assessments that we give at those various times. So if you're interested in learning more about the project or looking at some of the particular learning progressions or the professional development materials or any of the lessons, they're all up and available on our project website, so I'll leave that up there. But I'm happy to answer any questions at this point if you have any. I don't think I put too many of you to sleep, so hopefully
One of the